Welcome to the next video on matrix algebra. In this video, we'll discuss inverse matrices. To motivate the definition of an inverse matrix, let's go ahead and consider multiplying matrices A and B below. So I didn't say which order to multiply them in, so let's go ahead and do them both. So we'll start off with A times B. So that means I'm putting matrix A on the left and matrix B on the right. In the last video, we learned how to multiply matrices and to make sure that they are compatible. So we have a 2 by 2 and a 2 by 2 matrix here. So these are definitely compatible. And the resulting matrix is also going to be a 2 by 2 matrix. The way that I'm going to get each position in this 2 by 2 matrix is for this guy, the x11 position, the first row, first column. I'm going to take the first row of A, which is 3, 1, and I'm going to multiply by the first column of matrix B, which is 1, negative 2. So that's going to be 3 times 1 plus 1 times negative 2, which is going to be 1. So this entry right here is a 1. My x12 entry, first row, second column, is going to be the first row of matrix A and the second column of matrix B. So that's 3 times negative 1 plus 1 times 3, which is 0. And I'll continue this process for the second row first column entry and the second row second column entry. So what you notice is that when I multiply these two matrices, A and B, together, I end up with the 2 by 2 matrix that has 1s on the diagonal and 0s elsewhere. This is the identity matrix, the I2 identity matrix. Let's see if the same thing happens when we multiply these two matrices in the other order. Upon multiplying the matrices B and A with B on the left and A on the right, we see again that we end up with the identity, the 2 by 2 identity matrix. What that says about the relationship between the matrices A and B is that they are inverses of each other. If A times B is equal to B times A, and now those two products both equal the identity matrix, like we saw in the last example, then we say that A. So if A is any arbitrary matrix, then its inverse matrix is denoted with a superscript of -1. Not all matrices have inverses. If a matrix doesn't have an inverse, then we call that matrix singular. A matrix that does have an inverse is called non-singular. So let's talk about the technique for finding an inverse matrix. The first thing that you're going to want to do is you're going to want to put the matrix A into an augmented matrix with the identity matrix on the right-hand side of the augmented bar. Once you have A in an augmented matrix with the identity on the right-hand side, you're going to use your row reducing rules to reduce the left-hand side, reduce A, until it becomes the identity. So now your augmented matrix will have the identity on the left-hand side, and as you go through that process, your right-hand side will transform, and it will transform into the inverse matrix. Let's go ahead and put this method to practice. We saw these two matrices A and B earlier, and we saw that when we multiplied them, they produced the identity. So we know that they are inverses of one another. Let's go ahead and show that they are inverses of one another by putting A into an augmented matrix with the identity and row reducing it until our right-hand side becomes our inverse matrix, which is this B right here. So here's my matrix A, put next to the identity matrix, the I2 identity matrix. Now we want to turn this matrix A on the left into the identity. So my first goal is to get this 3 to turn into a 1. So I'm going to apply a row operation to row 1, and that row operation is going to be to multiply row 2 by -1, and then add that to row 1. So my first entry, my new entry in row 1, is going to be -1 times 2, which is -2, plus 3, which is 1. This second entry right here is going to be -1 times 1, which is -1, and then add 1, which gives me 0. Now moving over to these two positions, I'm going to have -1 times 0 plus 1, which is going to put a 1 right here. And then my last position is going to be -1 times 1, which is -1, and then added to 0, which is -1. So now my next goal in getting my left-hand side to be the identity is to change this 2 into a 0. So in order to make that 2 into a 0, I'm going to apply a row operation to row 2, and I'm going to take all of the entries of row 1, multiply them by -2, and then add them to the entries of row 2. So that first entry is going to be -2 times 1, which is -2, plus 2 makes 0, right? I knew it was going to be 0 because that's how I designed this algorithm. My next entry is going to be -2 times 0, which is 0, plus this 1, which is 1, which is good because if I remember, I wanted my left-hand side to be the identity matrix, and now it is. But let's see what happens as a casualty over here on the other side to these two positions. So I'll have -2 times 1, which is -2, added to 0 puts a -2 here. And then finally, -2 times -1 is +2. Added to this 1 gives me a 3. So because my left-hand side is now the identity matrix, this is my inverse matrix. So this shows that A inverse is equal to the matrix 1, -1, -2, 3, which we know is equal to the matrix B from earlier. So we have shown that A and B are inverses of each other. So we can say that A is non-singular because it has an inverse, and B actually is also non-singular because its inverse is A. And we could show that A is the inverse of B by putting the matrix B next to the identity matrix and going through the process again. What we would find is when we reduced the left-hand side, the B side, to become the identity matrix, what would pop out on the right side would be the inverse of B, which is our matrix 3, 1, 2, 1, which was the matrix A. So we can go through this process with much larger matrices. This is a pretty tedious process, so a lot of times you'll use some form of technology like a graphing calculator to find an inverse matrix, but this is the technique you use if you were going to do it by hand.